Mars, the fourth planet from the Sun, is often referred to as the red planet due to its iron-rich surface soil, which oxidizes and gives it a reddish hue. Beyond its striking appearance, Mars shares several intriguing similarities with Earth, particularly when it comes to axial tilt and seasonal variations. Understanding these aspects not only provides insight into Mars' climatic and environmental patterns, but also helps contextualize how these features influence its potential for habitability and past geological activity. Mars has an axial tilt, also known as obliquity, of approximately 25.2 degrees. This tilt is remarkably similar to Earth's axial tilt of 23.5 degrees, which is why Mars experiences seasons much like Earth does. The axial tilt refers to the angle between a planet's rotational axis and a line perpendicular to its orbital plane. This tilt is responsible for the distribution of sunlight across the planet's surface throughout its orbit around the Sun. Unlike Earth, whose axial tilt is stabilized by its relatively large moon, Mars lacks a significant natural satellite to act as a stabilizing force. As a result, Mars' axial tilt is far less stable over long timescales. Models and geological evidence suggest that Mars' obliquity can vary significantly, oscillating between as little as 15 degrees and as much as 35 degrees over hundreds of thousands to millions of years. This variation is due to gravitational interactions with other planets in the solar system and the lack of a stabilizing mechanism like Earth's moon. These fluctuations in axial tilt have profound implications for Mars' climate and potential habitability. When the tilt is more extreme, the poles receive much more sunlight, leading to significant sublimation of polar ice and possibly even liquid water activity in certain regions. Conversely, a lower tilt could lead to more extensive ice coverage, particularly near the equator.
Mars' tilt is currently very close to Earth's, which means its seasonal patterns are somewhat familiar to us. However, the differences in orbital eccentricity and rotational dynamics mean that the details of Martian seasons differ significantly from those on Earth. Understanding these differences requires an examination of Mars' orbit and the interplay between its axial tilt and orbital characteristics. Mars' orbit around the Sun is more eccentric than Earth's, meaning that its distance from the Sun varies more significantly over the course of its year. This eccentricity has a notable effect on the intensity and duration of the seasons on Mars. When Mars is closer to the Sun, it moves faster in its orbit, resulting in shorter seasons. Conversely, when it is farther from the Sun, it moves more slowly, leading to longer seasons. Mars' year is approximately 687 Earth days, nearly twice as long as an Earth year. Consequently, each season on Mars lasts about twice as long as its terrestrial counterpart. The combination of the planet's axial tilt and eccentric orbit results in asymmetric seasonal durations and temperature variations between the northern and southern hemispheres. Due to Mars' elliptical orbit, its seasons are not of equal length. The approximate durations of the Martian seasons are as follows: northern spring/southern autumn, 194 Earth days, the longest season; northern summer/southern winter, 178 Earth days; northern autumn/southern spring, 142 Earth days; northern winter/southern summer, 154 Earth days. This asymmetry is particularly pronounced in the southern hemisphere, where summers are shorter and hotter due to perihelion occurring during southern summer. Conversely, southern winters are longer and colder as aphelion coincides with the season. Mars' polar regions play a significant role in its seasonal dynamics. The polar ice caps are composed primarily of water ice and carbon dioxide ice, dry ice. Seasonal changes in temperature cause these ice caps to wax and wane dramatically. The northern polar cap is composed primarily of water ice, with a seasonal layer of carbon dioxide ice that forms during winter. As spring and summer arrive, the carbon dioxide ice supplements, exposing the underlying water ice. This process releases significant amounts of carbon dioxide into the atmosphere, contributing to seasonal changes in atmospheric pressure. The southern polar cap is more complex, with a thicker layer of carbon dioxide ice covering a smaller water ice base. The southern cap experiences more extreme seasonal changes due to the planet's orbital eccentricity. During southern summer, The carbon dioxide ice supplements rapidly, but the shorter duration of the season means less water ice is exposed compared to the northern cap. Mars' thin atmosphere, composed mostly of carbon dioxide, responds dynamically to seasonal changes. During winter, carbon dioxide freezes out of the atmosphere at the poles, causing a measurable decrease in atmospheric pressure. In spring and summer, the sublimation of carbon dioxide ice returns this gas to the atmosphere, increasing pressure. Dust storms are another prominent atmospheric phenomenon on Mars, often tied to seasonal changes. These storms range from localized events to planet-wide occurrences, with global dust storms typically originating during southern summer. The increased solar heating at this time creates stronger winds, lifting fine dust particles into the atmosphere and reducing surface visibility.
Understanding Mars' axial tilt and seasonal variations is crucial for future exploration and potential colonization. Seasonal changes influence surface conditions, such as temperature, radiation levels, and atmospheric pressure, all of which impact the design of habitats, rovers, and other equipment. Additionally, seasonal cycles affect the availability of resources like water and solar energy, which are vital for sustaining human and robotic missions. Moreover, the study of Mars seasons provides valuable insights into the planet's past climate and geological history. Variations in axial tilt over millions of years could have led to periods of more favorable conditions for liquid water and potentially life. Understanding these cycles helps scientists reconstruct Mars' climatic evolution and assess its habitability. Mars' axial tilt and seasonal variations reveal a planet with a dynamic and ever-changing environment. While similarities with Earth's tilt and seasons make it a familiar world in some respects, the unique interplay of its orbital eccentricity, thin atmosphere, and lack of a stabilizing moon creates a climate that is distinctly Martian. These features not only shape the planet's surface and atmosphere, but also provide critical information for understanding its history and planning for its future exploration.